All right, for our second topic here, we're going to look at exponential growth, specifically related to finance. Exponential growth relates to a lot of different concepts. It could be like radioactive materials, specifically not growth, but decay, going the other way. We're going to look at things getting bigger, but it can be about things getting smaller and smaller and smaller. It can be about used in medicine oftentimes for that same purpose, or in the growth of bacteria. They often exponentially grow. So something like even thinking to COVID would have been something that grew exponentially. One person had it. It's not one, then two, then three, then four, then five people had it. It's one person had it, then 10 people had it, then 50 people had it, then 100 people had it, then 10,000. Like, it just grows very rapidly and quickly. And this is what exponential growth is, something that increases constantly such that it leads to rapid growth. So exponential growth increases increasing constantly, leading to rapid growth. That is the key idea here with exponential growth. Why is it crucial to our personal finance? Well, simply put, it is compound growth. We looked at compound growth in the last lesson. Exponential growth is the kind of parent to compound growth. Compound growth is a type of exponential growth. So exponential growth is a type of growth that occurs at an increasing, there should have been an in there, an increasing rate, as opposed to linear growth, which happens at a constant rate. Increasing rate, we're looking at something that's curving upwards like this on a graph, where a constant rate is just going to be a straight line. So again, we're going 1, 2, 3, 4, 5, 6, 7, 8, 9 kind of idea with linear growth, where exponential growth may be 2, 4, 8, 16, 32, 64, and every step we're taking, we're going extremely bigger. In terms of the exponent portion of exponential growth, is that exponential, what's it having to do and relate with in what we're doing? It is related to time. It's that time of growth. The longer period of time we're growing money, the more money we're going to have. Or perhaps the bank, because they're also taking our money when we take loans and things like that. There is an interesting concept. So this is not, you don't have to memorize this one, but it is useful to know because it does come up and you may see it occasionally in finance. And that is the concept of continuous growth. And that's when growth is compounded at infinitely small intervals. So we're getting smaller and smaller and smaller, such that we can't get any smaller. This is the smallest possible interval of time. It's smaller than seconds or milliseconds or microseconds or nanoseconds. This is the smallest possible unit of time that could ever possibly be. We don't even have a word for it. It's just infinitely small. In this case, then we're looking at what's called continuously compounded interest. So continuously compounded interest is interest that is compounded at infinitely small intervals. We'll look at a formula in a moment. So the exponential growth formula, what is it? Well, it is A equals P1 plus R divided by N, all to the power of NT. Look familiar? Hopefully it does, because it was the same formula as the compound interest formula, because it is the compound interest formula. Exponential growth and compound interest are the same type of thing in terms of finance. Just to give you some separate names, so you can refer back to the first note if you need to, but to give you some separate names, A refers to the future value or the initial amount. P, the principal or initial value. Initial may be replaced with starting or first value. The R, well, that's fairly consistent. It's the rate of interest. So often just R for rate. Again, remember that is always annual. T is the number of years, the time in years. And N is the number of compounding periods per year. So if it's weekly, it's 52. If it's monthly, it's 12. If it's annually, it's 1. Things like that. Very similar. Again, I just gave some separate terms for some of those that you may hear occasionally. Now, the continuous compound growth formula, it's a little bit different. It's A equals P ERT to the power of RT. RT and P and A, they're exactly the same as the compound interest formula. What changes is E. This is called Euler's constant. So that's Euler's constant. This is a very specific constant number like pi, where it never changes. It is 2.71828. Again, it relates to the infinity of smallness that we are working with. This is how this formula, as we change n to a bigger and bigger number, meaning a smaller and smaller period, from days to minutes to seconds to nanoseconds and so on, this is where the formula ends up. Again, not commonly used in personal finance. This is more of for finance managers, things like that are doing calculations to see how much money is potentially possible to make at the maximum. So let's look at some practice problems. We'll go through them fairly quickly. In each case, we want to list our values that we know and need to find. So we're looking at the basic exponential growth of just $1,000. We want the future value of that, or the A value, the final amount, invested at 5% annual for 3 years. Each of these questions, by the way, is just at an annual interest rate, so annual compounding. We're not going to use any of the various n's, so our n is always going to be 1. So we're looking for A. P in this case is 1,000. T is 3. And n is 1. So there's the values that we know. Our formula, A equals P 1 plus R divided by n to the nt. Filling in those values, A equals 1,000, 1 plus 0. Oh, we missed the rate here, sorry. So the rate here is 0.05. We also need the rate, because if we don't have the rate, we can't do our calculation. Divide that by 1 to the 1 times 3. Calculate that out. The divided by 1 just leaves us with 1 plus 0.05. The times 1 gives us a 3 up top. So we have A equals 1,000, 1.05 to the 3. This only happens where it's nice and exactly 0.5, and the 3, why they're exactly the same, is only because it's a 1, it's annual. If it was a day, week, month, anything, it would completely change the number. Working that out, however, we got 1,157.63. Thus, we have made $157.63 worth of interest on top of the initial $1,000 that we started with. So remember, this is the final amount, not the total interest. The interest is only whatever we started with plus the extra here. So in this case, $157.63. Looking at some comparative analysis. So if we compare different interest rates and how those will affect how much we earn. Starting again, our amount, we don't know. Our principal rate in this case was $500 at 3 versus 5%. So 500, our rate is either 0.03 or 0.04, depending on which case we're looking at. Our time is 5 years, and again, we're just using 1 for our compounding periods because it doesn't specify anything different. At 3%, we would fill in our formula, and I'm just going to skip some steps to make it easier for the note. Here, you should usually write out the formula until you have it down pat and don't have to think about this at all. 500 times 1 plus 0.03 to the power of 5. Notice I skipped the divide by 1, the times 1, because they're not going to change anything. This is only, again, the case because it's annual. And again, just to make it easier for us to write out, I know you're writing this note at home and don't want to write a lot. So there's our 1 plus 0.03. And when we work that all out, we get 579.64. I'm going to take a little bit more of a shortcut here on number 4, again, because we've illustrated the full process up here. We know that we're going to just change the 0.3 to a 0.4. And so when we add everything up, we're going to get 500 times 1.04 to the 5. If I take that and work it out, I get $608.33. And so over that 5-year period, on just simply $500, we've made an extra approximately $30, which doesn't seem like a lot of money, but in the case here, I mean, like we only had $500 over a long period of time, maybe 20 years, 30 years if you're investing for retirement. If you have more money, $5,000, that all of a sudden becomes $300 of difference. Now it starts to become significant. We're starting with small numbers, but as we increase either time or the initial value, that will also greatly increase the difference between those two numbers. But definitely 1% difference is significant. Finally, last practice problem here, just comparing that concept of continuous versus discrete compounding. So our A, again, we're looking for the principal. In this case, we have $1,000 compounded annually at 5%. So our rate is 0.05. Our time is 2 years, and our number of periods, again, is 1. Filling in our compound interest formula, so for the annual, we have A equals 1,000 times 1.05 to the power of 2. And again, I'm just cheating the formula a little bit here for the sake of time and length of the video, but we're going to get 1,102.50. So it made $102.50 of interest. Not too shabby. If we were to do this continuously, then the formula changes. So it's the P equals E to the RT. So 1,000 times 2.71828, and then the rate 0.05 times 2. If you type this in your calculator, you can either type in this number just like pi. There also is an E button on most every calculator that has a pi button. So if you have a pi button, you probably have an E button that you can press to get the exact value. And when you work that out with the exact value, pressing the E button on your calculator, you will get $1,105.15. Just a little bit more. Again, this is a short period of time, so you're not going to see a significant difference between the two numbers, but continuous over a long period of time would be more. Just to note, if you were to calculate the compound interest monthly, you would still only get $104.94. It's a little bit more here as we're increasing the time. The more times per year it's compounded, the more money you're going to make. So infinitely, the most money you could possibly make on $1,000 at 5%, if you compounded it every single instance of the universe, you would still only get $1,105.17. That is the maximum possible value versus if you do it annually, which is more apt to what you would get in terms of an investment. Okay, so just a couple things to review. Importance in personal finance of this compounding exponential growth, and that is money grows over time due to exponential growth. So that's the compounding. That's what happens. That compounding is caused by the exponential growth. When we have loans, the interest on loans can be growing rapidly. So interest can grow rapidly over time because of that exponential growth. Remember, that's that not just growing nice and easy and straight. Let's see if I can focus. There we go. Instead of growing straight like that, it goes quickly up and keeps getting faster and faster in terms of growth. The more time, the quicker it grows. And then finally, in terms of planning for your life, when you're planning for the future, it is important to consider that exponential growth. And why do we consider exponential growth? I didn't leave enough space here in this line. I should have made a really long line, but it can significantly the value of loans or investments. Ran a underpaid figure. So the value of loans can be significantly decreased if you understand this, how it works, paying off things. And then it can also it can increase how much you're making or how much you're paying in terms of long term. So that's everything on exponential growth.